All right, guys, welcome back. Now, this is where it's going to get really fun. Yesterday, you learned how to find the determinant of a 2x2 matrix or a 3x3 matrix. Now, using only determinants, you can solve 2x2 systems of equations or 3x3 systems of equations. So goodbye substitution and elimination method. Check this out. Okay, when they have the two vertical lines on the outside of a matrix, this means that they want you to find the determinant. Remember, it's just that single number. So if you want to take a 2x2 system and solve, meaning you know if you graph these two on a coordinate plane, where would they cross? You have to solve for both x and y. Step one, you would go ahead and find your coefficient matrix. So that's what's showing on the bottom here. That's going to be the denominator. You take your coefficients of x, they go in the front. Coefficients of y, they go in the back. Notice it's the same thing for both x and y. You find your determinant. So the determinant of the original coefficients is on the bottom. Now on the top, notice you're finding determinants again. If you are trying to solve for x, the solutions, whatever your equations were equal to, they would go down the x column. You're not solving for y, so your y values would stay the same. Then you would find the determinant of the top, divide it by the original determinant, and that's your x value. If you're trying to find y, then you take your solutions and they go down the y column. Whatever variable you are trying to solve for, that's where the solutions go. I'm not solving for x, so notice your x coefficients stay. It's just the one that you're trying to solve for. The solutions replace the original. Find the determinant of the top, divide it by the original determinant, you solve for y. Okay, so let's go ahead and try example number one. Example number one is a 2x2, okay? So step one, you're going to take your original system and turn it into, remember that coefficient matrix? So your x's are 2, 1, your y's are 3, 1, and it's just a 2x2. Again, it's not like an augmented matrix. You do not use the solutions. The solutions come in later. So the 2 and the 1, the 3 and the 1. To find the determinant, 2 times 1 is 2, minus 3 times 1 is 3. 2 minus 3 is negative 1. That's your determinant. Now, if you are trying to solve for x, you take the solutions. The solutions are 0, negative 1. They go down the x column. Remember, it's x, then y. I'm not solving for y, so I keep my original y values 3 and 1. I'm going to find the determinant, that's why it's in the vertical lines, and then divide it by the original determinant, which we found to be negative 1. 0 times 1 is 0, minus 3 times negative 1 is negative 3. If you're minusing a negative, this is really 0 plus 3 divided by negative 1. 0 plus 3 is 3. 3 divided by negative 1 is negative 3. So x is negative 3. Now to find y, you need to know what y is. So the solutions go down the y column. And remember, it's x, then y. So the 0, 1, they go in the second column. I'm not solving for x, so the original x's, 2 and 1, stay. We have to find the determinant of the top and divide it by the original determinant, which was negative 1. 2 times negative 1 is negative 2, minus 1 times 0 is 0. Negative 2 minus 0 is negative 2, divided by negative 1. Negative divided by a negative is a positive. 2 divided by 1 is 2. So your solution, the x is a negative 3, the y is a 2. You just solved that system of equations by only finding determinants. You did not have to do the substitution method or the elimination method or graph on a coordinate plane and see where they crossed. So this just provides us with one more way, one more method of solving a system of equations. So here's our example of a 2x2. Now we're going to step it up and let's go ahead and do a 3 by 3. Now if you remember, a 3 by 3 is kind of a big process. When we solved it using elimination method, what you had to do was pick two equations, cancel a variable. Pick two different equations, cancel the same variable, then use substitution or elimination at that point to go ahead and solve the remaining, which was a 2 by 2, then substitute back in. The other way that we solved a 3 by 3 is we created an augmented matrix, and then you had to do Gauss-Jordan elimination where you had the ones on the diagonal and then you got the zeros by creating that map. So this is just going to give us a third way that we can solve 3 by 3 systems. Now it's very, very similar, okay? Step 1, what you are dividing by. Notice they kept the x's, so it's a sub 1, a sub 2, a sub 3. Those are the coefficients of x. B sub 1, B sub 2, B sub 3, those are the y's. C sub 1, C sub 2, C sub 3, those are the coefficients of z. They're in the vertical lines, meaning you have to find the determinant. So when you find your original determinant, you do not use the solutions at all. You use the coefficients only, find the determinant, that's what you divide by every time, whether you're finding x, y, or z. Now what you figure out on the top, if you are trying to solve for x, your solutions go down the x column. The y's and the z's would stay the same. Find the determinant of the top, divide it by the determinant of the bottom, that's x. When you go to solve for y, the solutions go down the y column. The x and the z's would come from the original system. Find the determinant of the top, divide it by the determinant of the bottom, that would be your y value. When you go to solve for z, now the solutions will go in the third column because remember it's x, y, z. So the solutions go down the z. The x's and y's stay the same. Find the determinant of the top, divide it by the determinant of the original. That would be your value for z. Now obviously this is going to take a little bit more time because it takes more time to find the determinant of a 3 by 3. But we have got this, guys. Okay? So step 1, we have to find our original determinant. So you take the coefficients how they are. So x has a 1, a 3, and a 2. Y has a -1, a 1, and a 3. Z has a 2, a -4, and a -4. Remember, if it is a 3 by 3, you have to take the first column, rewrite it on the outside, take the second column, and write it to the right of the first column. Now you do your diagonal lines. 1 times 1 times -4 is -4. Plus -1 times -4 times 2 is 8. Plus 2 times 3 times 3 is 18. -4 plus 8 plus 18 is 22. Now you start from the bottom. 2 times 1 times 2 is 4. Plus 3 times -4 times 1 is a -12. Plus -4 times 3 times -1 is 12. So I get a 4. Your determinant is the first sum, so 22, minus the second sum, which is 4. 22 minus 4 is 18. That's your original determinant. So each time you will be dividing the new determinant by 18. Now let's go ahead and solve for x. So if I am solving for x, my solutions, what you had on the right side of the equal sign, they go down the x column. So -4, -6, +4. The y's stay the same, -1, 1, 3. The z's stay the same, 2, -4, -4. I have to find the determinant of the top and then divide it by 18. Again, the top is a 3 by 3, so the first column has to go on the outside. The second column is rewritten to the right of the first column. Your diagonal lines. So -4 times 1 times -4 is 16. Plus -1 times -4 times 4 is 16. Plus 2 times -6 times 3 is -36. 16 plus 16 plus -36 is -4. Now you go from the bottom. 4 times 1 times 2 is 8. Plus 3 times -4 times -4, that's +48. Plus -4 times -6 times -1 is negative 24. 8 plus 48 plus a negative 24, that's 32. 32. So now your determinant, the first sum, negative 4, minus the second sum, 32. So negative 4 minus 32 is negative 36. That's the determinant of the top. To solve for x, you have to divide it by your original determinant, which we found to be 18. So negative 36 divided by positive 18 gives us x. X is a negative 2. Now to find y. So y equals, this time I'm solving for y. So the solutions go down the second column. Negative 4, negative 6, 4. The reason why they're here is because this is the y column. This is x, y, z. The x's stay the original. 1, 3, 2. The z's, 2, negative 4, negative 4. We have to find the determinant of the top, divide it by the original, which is 18. So I rewrite 1, 3, 2, and negative 4, negative 6, positive 4. Now again, you start with your lines. 1 times negative 6 times negative 4 is positive 24, plus negative 4 times negative 4 times 2 is positive 32, plus 2 times 3 times 4 is 24. 24 plus 32 plus 24 is 80. Now you start from the bottom. 2 times negative 6 times 2 is negative 24. 4 times negative 4 times 1 is a negative 16. Negative 4 times 3 times negative 4 is 48. Negative 24 plus a negative 16 plus 48 is 8. The sum from the lines going from the top, so the first sum was 80, minus the second sum, which is 8. 80 minus 8 is 72. So the determinant of the top is 72. To solve for y, now you have to divide it by the original determinant, which was 18. 72 divided by 18 is 4. So y is a 4. Now to solve for z. If I want to solve for z, the solutions, the negative 4, negative 6, 4, they have to go down the z column. Your x's, 1, 3, and 2, and the y's, negative 1, 1, and 3. These stay the same from your original problem. We have to find the determinant of that 3 by 3, divide it by the original, which is 18. So I take the first column, 1, 3, and 2. Then I take the second column, negative 1, 1, and 3. Now I start with my diagonal lines to determine what the determinant of the numerator is. 1 times 4 is 4, plus negative 1 times negative 6 times 2 is positive 12, plus negative 4 times 3 is negative 36. 4 plus 12 minus 36 is negative 20. Now you do the same thing from the bottom. 2 times 1 times negative 4 is negative 8, plus 3 times negative 6 times 1 is negative 18, plus 4 times 3 times negative 1 is negative 12. Negative 8 plus a negative 18 plus a negative 12 is negative 38. Take the first sum, negative 20, minus the second sum, negative 38, minus a negative. This is actually a plus. Negative 20 plus 38 is 18. Now you take this determinant, divide it by the original. 18 divided by 18 is 1, so z is a 1. So your ordered triple, your x is a negative 2, your y is a 4, your z is a 1. We just solved a 3 by 3 system of equations by doing nothing other than finding determinants. So this is called Cramer's rule. It gives us another tool for our tool belt, ways that we can go ahead and solve systems of equations. Again, today you have a short worksheet where you can practice these skills on your own. I hope you enjoyed learning something new today, and I'll talk to you soon. Bye, guys.